Okay. Okay. Let's check if we have any social media update. Okay. Okay, well, let's wait maybe a few seconds. I'm sharing the link with some people that were interested. So I'm waiting just a second to start. A few seconds. Well, the idea for today is to have a quick demo, a quick overview of how we made the integration of Cairo Native into our Sonic and Rust engine, and that engine used from Lambda class stack. So to start, let's start with Aki with a quick intro of Cairo Native maybe, and then we will show the demo, some code, and we'll run some tests showing how the thing is working. And well, I hope everything works today. So, Aki.
Absolutely. So just to give a little bit of background context, let me share here. So as people may or may not know, if they're interested, Cairo Native is a project the goal of the project is to be able to run Cairo programs and contracts natively on a CPU. And the way to do that is to take the intermediate representation of a Cairo program called Sierra, which has certain guarantees and a certain nice structure that we can process, and translate that into executable code that the processor can run. And also provide the execution context with which to run that code, right? So to do that, well, we have this crate. The crate depends on the LVM and the Rust bindings to the LVM. And what it does is it takes the Sierra representation and translate that into in-memory data structures representing that program, and which you can then process using LVM to either lower it down to various other representations. So in our README, for example, we have command line interface usage. These are not meant for development, like user development, more for debugging purposes. One of them is the Cairo Native dump, and what that will allow you, if you provide it with an input Cairo program, it will translate it, do the entire compilation process, and then dump that to disk so that you can take a look at the textual representation of the program, kind of how it looks in memory before you execute it. And if you actually want to execute it, then you can call on Cairo Native run, which wraps all of our libraries in an easy to use way. And it's also interesting because if you look at the implementation of Cairo Native run, then you can get like a feel for a running example, right? It's pretty easy to use. The things you provide to Cairo Native run are the input and the outputs for your program, the available gas, and obviously the program and where you want it to start, the entry point within the Cairo contract. So there's also some supporting documentation in the developer guide, and then you can see some facilitating scripts, to run the JIT, run the execution. So you've just provided the Cairo and the entry point, and then there's a JSON input which represents the input to the program, and you can have it run, which the guys will demo shortly. But more interesting than this, because this is all like from the outside, is how would you use it as a developer to actually run, to incorporate Cairo Native into your program. And for that, we have an example called the easy use of the API, the simplest use possible. What this does is, for demonstration purposes, we give it a Hello Cairo program, which just does the hello world. It prints out the username. And what you need to do is, you need to, as I said, it doesn't take Cairo, it takes a Sierra representation. So we have a utility function that compiles the Cairo to the Sierra. If in your context you already have the Sierra representation, that's fine. You can just take it. And once you have it, you have to instantiate the native context, which would be like a wrapper around all the compilation infrastructure. Once you have a native context that you can use to compile Sierra to native code, then you can give it the reference to the Sierra program and ask it to compile it. What this will return is a native module, which wraps not only the executable code, it's already compiled, optimized, and lowered to native object code, but also all the metadata related to the compilation process that you can also use to run. You then prepare the inputs. In this case, what we want to provide a short string representing the username, in this case, user. We also need to specify the function that we will want to run from this program, in this case, the entry point. So this is the module name, and this is the function name. You need to wrap that and serialize it, and then also provide it an object which will know how to deserialize the results of the execution. You need to get the function ID, which is the index into the program. You can ask that from the database with this utility function. And also you need to know whether that utility, the entry point requires gas or not, and if it does, what gas. So once you have all that setup done, you can then instantiate a native executor and give it the native program. And just call execute, and it will return a struct with all the calls and the results. You will obviously have to do some error handling, which obviously depends on what use case you have. So in this case, it's exemplified. But that's pretty much it. So the basic steps are easy to use. Just you need to have your Sierra program, instantiate a compiler, give it to compile it, and then instantiate an execution environment, the executor, and give it the compiled program, and then you can just go. I'm gonna stop sharing. That's the basic flow. Obviously, for something more involved, because this is just like a standalone program with one entry point. If you have multiple entry points, if you have something like a contract with events, etc., something that calls into an external execution environment, that's a bit more involved. But we have also examples on doing that, which is exactly what we want to. But this is background. This is the basic use.
Okay, thanks, Aki. So now to continue, maybe Javi, let me check while you're sharing the screen. How can I arrange the windows? Because I didn't want to interrupt Aki.
Oh, sorry.
Are you sharing? No.
I am about to. Is it working?
Yeah. But
okay, cool. Can you see?
There are just
yeah.
Yeah, but let me check so I don't. What's the best? No, I think that the best is to maximize your window. Okay, let's do that.
Okay, cool. Yeah. Okay. So the idea now is, after presenting sort of what Cairo Native is in a vacuum, the idea was to actually plug this into StackNet in Rust. So the idea here is StartNet in Rust is like an execution sort of like engine for StartNet. So what it's used for is if you ever like submit a transaction or anything to StartNet, that has to get executed. And that's what StartNet in Rust is for, essentially executing transactions and deploying contracts, that sort of thing. So underneath that will use, of course, the VM or Cairo Native, because that requires executing Cairo code, but it also requires interacting with like an environment, like essentially the blockchain state, and that's what this is for. So you got Cairo Native, and as Aki said, you have to interact with like a sort of like a runtime environment on top, which manages the state. And for that, that essentially means implementing what StartNet calls syscalls. So syscalls are these calls to that environment that manages state. So that's essentially what we had to do to integrate with it. So here's essentially the code for it. This is StartNet in Rust, and this is like the main execution function that gets called whenever you want to make a transaction, you want to execute some code, or think about transferring an ERC20 or deploying a contract, that sort of thing. So what we did is we went in here and we took the normal logic where you're essentially getting like, you can think of this as the state of the blockchain, and then all the context, all the execution context of that blockchain. And here you're looking, the contract you want to execute and its function. And before integrating with Cairo Native, this was all executed eventually by the Cairo VM, which is what you're seeing here. So this here you're matching the contract class, and usually you would get the chasm, and eventually you would execute it, and you would execute it with the VM. So what we did is we went down here and we added this match where like now if you get some Sierra code, you fall in here and you do a bunch of stuff, but then eventually you call this native execute function, which will call Cairo Native. So it'll execute whatever function is meant to be executed with Cairo Native. And this is using essentially the API that Aki showed before, where you instantiate a native context, you compile it to a Sierra program. Eventually, this compilation might not happen here, but for now it is. But you're essentially doing all the stuff Aki just showed, but you also pass this syscall handler, which is sort of like the handler that will manage these syscalls. So you can think the most basic example of syscalls are like reading or writing from storage. So if you want to, I don't know, like transfer ERC20s to someone else, that will mean essentially writing to the blockchain storage to deduct some tokens from yourself and give them to someone else. That's managed by this syscall handler. But the rest looks the same. So you instantiate the native module, etc., what Aki just showed, and then you execute it. You were parsing call data, whatever. But eventually we execute with the executor, and we get a bunch of info which we pass back to StartNet in Rust, so that they can manage it with the result of execution and whatever other information. So we added all this, and to test it as like our basic test, we essentially managed to get an entire ERC20 contract working. So here we have an integration test for that, which does what you would expect. So we're reading the Sierra ERC20, and then we just do all the necessary preparation stuff with like simulating the state of the blockchain, inserting the program into the state and all that stuff, so that eventually we can call it, and then we start calling the contracts functions. So first we call the constructor here with all the call data, and then we start asserting that everything worked as expected, and then one by one we call the method. So we get the total supply, and total supply should be 4, because when I call the constructor, I call 4, etc. So we call total supply, decimals, all the methods you probably know from your C20s. We are calling them and making sure that the result is the expected one. Balance, allowance, etc. We approve, we transfer tokens, we make sure that after transferring the balances are what they should be, etc. So I can, just to show it, I can run it here. And I added a bunch of prints to see the result of this. Not sure what we're compiling here, but it should be okay. It should just take a second. But I added a bunch of prints to show, the calls to the syscalls and, through MLAR. So you can see here, we are, going through it all. Once it ends, I'll go back to the beginning, but it's pretty self-explanatory. Okay, now we're done. So you can see here, so we started calling the constructor. This is printed by starting in Rust, but this is the name of the constructor. They're all they all have these weird names because they're sort of like how Sierra calls internally these methods. But you can see we call the constructor, and when we do that, we are calling a bunch of syscalls. So as I said, storage write. This is essentially writing all those values into storage, like initial supply, the name, the symbol, all those things. These are the calls for that stuff. And then, you're also emitting an event. So this is calling emit event. And then we go one by one. We call total supply. We're reading that total supply. If you see here, you can see this address we're reading from is this one, which makes sense because this is, this is the total supply that was written by the constructor when we first called it. And, same goes for all these other methods. There's a few so for example, increase allowance also calls this get execution info syscall that gets all the information from the environment, like the current block and all that stuff. We implemented those. They're all working. So you can see them here. That's where we're at here. We managed to make ERC20 working. There's a few syscalls we still need to implement, but we can talk about that at the end. But it's all working. That's sort of the integration with Start in Rust. Yep.
Okay. Thanks, Javi. Well, I think that the next step, what we've been working in this last few weeks is having the possibility to choose from starting with Rust whether to use the VM or native. So as we told, now the idea is to show that used from a standard stack. Maybe Nacho Ignacio, if you can
Sure. Let me share my screen as well.
And let's give a quick reminder of what the standard stack.
Yes. Just sharing. Can you see it? Oh, not yet. Okay. Yep. Okay, so you can see now, right? Okay. Cool.
No, we're not. Are you using? Okay. Sorry, my bad.
Sorry. Yeah. Okay. Yeah. So the next abstraction step in this chain is essentially to show Starnet Stack. A Starnet Stack is a way to run blockchains easily, specifically Cairo compatible blockchains. Here's a diagram that shows how it works. It's essentially comprised of 3 main components: the sequencer, the watcher prover, and then the explorer and the verifier. The sequencer is essentially a sequencer running a consensus algorithm In this case, we have an implementation of hot stuff, which provides transaction ordering and block production for incoming transactions, right? That sequencer is right now running standard in Rust with Cairo Native through the integration that Javi was mentioning. Essentially, we are using standard in Rust to provide us with an easy way to execute transactions and keep the state of the blockchain, right? So the client can send transactions to the sequencer, which will execute them with Cairo Native on standard in Rust, and then it will settle them into blocks, which can then be queried by the watcher prover, which is another pool of processes which is watching the blockchain advance, and then it will request blocks from the blockchain and try to prove the transactions with the LambdaWorks Star Platinum prover. In this case, we need the watcher prover to run Cairo VM instead of Cairo Native because we want the trace as an output of the execution to have it proved by the prover, right? So yeah, once the watcher prover successfully proves a transaction or a block, it will store the proof on a specific implementation of storage, which can be like on AWS S3 or on the file system. So the third part of this chain is like the user can use the Explorer to see where the blockchain is at, and to also verify the proofs from the watcher prover, which will be retrieved from the storage in browser, because the verifier is browser compatible. You can run it essentially on the Explorer and have the transactions verified on the spot. So that's a summary of how Standard Stack works. We have a simple way of running everything locally, which is a make target called run local, which I'll run right now. What it will do is, let me run it. What it will do is essentially run a bunch of these processes, specifically 4 sequencer nodes, the watcher prover, and the explorer. And it will also launch a client which will send the blockchain a bunch of transactions to seed it with meaningful data. Which I think everything started right now, and the client is starting, so we'll see a bunch of sample transactions going on. And I think at this point we can actually query the logs from the sequencer node, and then we will see a bunch of information related to the consensus, but also between those logs lines, we'll see like some related to MLIR, which are coming from Cairo Native, from within standard in Rust, right? And I think we will also have like Cairo Native. We will show some outputs from transactions. These don't make too much sense without context, but they are essentially the results from the executions of the transactions that we have on the left pane here. So I think I can come back right now and see the Explorer running. It will run on localhost, and yeah, we can see incoming blocks with the new transactions. You can see in the overview that it hasn't been proven yet because this is the latest block from the blockchain. But if we go back to maybe block number 10, yeah, the proof is retrieved from the proof storage and then verified by the in-browser verifier. So what this means is essentially that going back to our diagram, that the watcher prover has successfully requested block number 10 from the blockchain, and then proven it and stored it on storage. And then the explorer is going to storage as well, retrieving the proof and verifying it. So yeah, that's the whole flow. To show a little bit of the code, we have our own implementation of the hot stuff node here, and you can see that it will have an execution engine. This execution engine right now, the only alternative is to run standard in Rust. We used to run the Cairo VM and Cairo Native by themselves, but we want standard in Rust because essentially it will provide us with a lot of things to easily maintain a state for the blockchain, right? And here's the implementation for that. It will have some preloaded contracts as well to make it easier to run in both transactions. And yeah, I think that's pretty much it for Starnet Stack. Yeah.
Okay, thanks. We want to stop sharing. Yeah. Okay, well, thanks. I was checking while sharing the link. Well, the other thing that we want to discuss here is next steps. What do we have missing and what to continue? Also, in Telegram, they are asking us about benchmarks. Maybe we can address the benchmark question first. I don't know, Aki, if you want to tell or Javi. Do we have any benchmark? What did we benchmark at the moment?
Well, we have an extensive benchmark suite that runs on different architectures, x86 and ARM. One of the things that there's quite a bit of variation depending on what the program does. Of course, it's sometimes hard to benchmark like integrate like all over the execution profile of a compiler. So we have a lot of different programs, and then we benchmark specific implementations of the libfuncs. We do one type of benchmark that does like end-to-end, like it compiles an entire program, runs it runs it several times, and, runs statistics and kind of like averages it out. And then we have some more like criterion benchmarks for specific pieces of code. In general, when you say, okay, but what does it mean? What numbers do you get depending on what the program does? If it's mostly compute bound, then you get somewhere in between, let's say, 20 and 300x improvements versus running the same program within the VM. One of the things that would be like next steps would be to improve our benchmark suite to include these new Cairo contracts, right? To see how much actual speed up we get when you're interacting with your host OS context. Like if the generate program is just compute bound, obviously that's much faster. If it has to call into the calling context, that has a bit of overhead, but not much. Exactly how much is one of the things that we should determine next.
Okay, great. Well, besides that, I think that on the regarding integration with the starting Rust, I think that we have some cache that we need to add for it to make it work to obtain the gains that Aki mentioned. So this benchmark that Aki mentioned was using Starlink in Rust. Cairo Native standalone. Yeah, solver. Yeah. We haven't benchmarked yet. I think after integrating it with the Starlink in Rust. Exactly. We need to do that benchmarking, but we wanted to add first a cache there. So,
as always, when you benchmark, one of the most important things is to be very explicit on exactly what you are measuring.
Yeah, sure. I don't know, Javi, if you want to add something.
Yeah, I would add that on top of that, we also need to, on the integration side itself, we need to, as I mentioned, implement a few more syscalls. They're about 6, and they're pretty straightforward, really. We also need to handle errors when executing better. So any call to a Cairo function can panic. It essentially can panic, and we are not currently handling that yet. So we need to handle that, which essentially just involves correctly parsing the result that we get from MLIR. And then I guess the last thing is just this is on the README on Cairo Native, but there are libfuncs to be implemented yet. You can find the list on the README. Those also need to be finished. But those are the 3 main things I would say.
Okay, thanks. I don't know if anyone wants to add something? Okay, some of the team is missing here, so thank you also to them to get to this point with the hard work of too many people. So thank you everyone, not only the ones in this call, Edgar and Steve for sure, but many other people worked in this project also. I'm checking if I have any message with some questions. Sorry, I'm checking the social network, social media. Okay, no, I think that's it. Yeah, that's it. Thank you all. I hope. Well, I hope this was useful for everyone, and we still have some things to address to make it completely useful, and we will do that in the next weeks. So thank you everyone, and enjoy your weekend. Bye.
Goodbye, everyone.
See ya.